Okay, good morning, everybody. I'm here at the PASC conference in Lausanne, Switzerland, and I have the pleasure to have a quick chat with Chris Johnson, who is professor at the University of Utah, director of the Ski Institute. So, Chris,
Good morning.
good morning to you. Yeah, thank you for accepting to have this little chat with us. Uh, tell me about your impression with the PASC conference here. This is the first time you are invited here at the conference. You gave a plenary lecture on Monday, and it was extremely well attended. I think I counted over 300 persons, so big interest in your work. Tell us more.
Well, thank you very much. And this is my first time at the PASC conference here in Lausanne, and it's been very interesting. And I was surprised at how many people are at the conference. Apparently, it's grown quite a bit over the last
Yeah.
few years, and it's really a nice set of areas. So there are people who are in high performance computing and scientific computing, and then a lot of applications areas.
Yep.
So there are a number of mini symposiums that are in. I went to a session on computational cardiology, and there's computational materials science and climate, and a lot of interesting applications. And fortunately, they all need work and help with visualization.
Yeah.
And so that's where I come in.
I think you started your career with bioengineering, right? Because you mentioned the cardio-related applications, but then the Ski Institute now has grown to really an immense workshop of how many different application areas do you have represented at the Ski Institute?
So our main core research areas are in visualization and image analysis and scientific and biomedical computing. But within those research areas, we have collaborations with people in neurology and cardiology and material science and mechanical engineering and English and poetry and other areas. So I think you would count tens of different application areas that we work with domain scientists or other application people in different areas.
Yep. Is it difficult to get students coming from a computer science background or a computational background to interact with the other application areas?
It's something that we feel is really important and but it's also very hard to do. So effective collaboration is a challenge for anybody. But I think we have figured out ways to help those collaborations be successful over the many years that we have done them, and it takes a lot of work and a lot of effort. But I think we've kind of figured out good ways to do that, and so there's an environment that's there where students come in and they can see how other people have had effective collaborations, and they're brought into groups or smaller subsets of teams that are working with domain scientists or engineers or people in medicine, and so they kind of learn how, as an apprenticeship in a way, of how to become a good collaborator over time. And we have students who are in computer science and bioengineering and mathematics and physics and bioinformatics and electrical and computer engineering, a number of different areas. So we're very interdisciplinary by ourselves. And just the structure of the institute where we have the students sit, we don't have the concept of like Professor X's lab and Professor Y's lab. All the students sit in different student spaces, and it's basically just, and you have bioengineering students sitting next to a physics student, sitting next to a computer science student. So when one of them graduates, whoever's next comes and gets that desk, and that also really fosters this interdisciplinary
There is cross-fertilization.
nature.
Yeah. Okay. So one of the components of the PASC conference we shouldn't forget is high-performance computing, right? High-performance computing today has a very well-defined frontier, the exascale frontier. What is your next frontier in the scientific visualization area? Is there one particular area that you like to focus on?
Well, so we have people who are working on the scientific computing part in exascale. Martin Berzins is the person at the Ski Institute who's really leading that effort and has been scaling this problem-solving environment called Uinta that does fluid dynamics and particle methods and everything, up to hundreds of thousands of cores on the biggest machines. And then, of course, they need visualization to be able to visualize this. And certainly one of the most important or interesting areas for visualization now in exascale is in situ. And so we are working on in situ from many different points of view. There are so many different questions to ask and try to answer yet, and it's a combination of analysis, of visualization, of user interfaces, of all kinds of things, of architecture, all have to be considered when we're thinking about this. And from my own point of view, I also think about uncertainty, because we're going to make all these decisions, and there's going to be uncertainty in the pathway, and how do we put in that and make that understood as well. So I think that's going to be a really interesting and challenging area for us in the future.
So supercomputing leads to big data, but I actually see a lot of small devices now being used for visualization. So can we compress, can we synthesize big data in meaningful ways for scientists to manage?
So my own view is that big data is dependent on the size of the system that you're working on.
Yes.
And so for the biggest supercomputers, it's exascale, but for your phone, it's a different size of data. And so I think there are big data problems at every scale of architecture and device that we have. And I think that there's a tremendous amount of work that we can do on going between the scales in terms of the pipeline of where we're doing the computation, where we're doing the graphics, how much is done on a server, how much our way we do compression to get images and interaction. And I think there's some really, really exciting and useful things that are going to come from that line of research of where we break the pipeline for what different particular architecture and device and application area, and that's still an unsolved problem as well.
One last question, perhaps. Scientific visualization has been enabled by the development of extremely powerful GPU, graphics card, for the mass market, right?
Yes.
So animation, special effects, etc. Where do you see the role of special effects in scientific visualization?
And for special effects, I think that the role there comes from, they're always pushing the envelope to try and come up with more realistic effects. And we're always pushing the envelope for more accurate representations. And in the beginning, those two were pretty far apart.
They were,
but I think that they're becoming closer and closer and closer. And a lot of the special effects people are really using scientific computing codes to do some of their special effects for fire and for other things. And that we can learn from some of the things that they're doing in terms of trying to speed up and make approximations and make things faster and more interactive, to maybe make our codes faster and more useful as well. And so I think they're actually coming together more than they're going apart, and we can learn from each other. So that, I think that some of the people that go to SIGGRAPH, who are doing mostly the special effects things, some people are going to the visualization conference. Maybe we should have a workshop on getting those people together on, sci-viz and special effects.
Okay, so perhaps this is something the PASC conference itself could take upon. Anyway, I'm going to thank Chris Johnson this morning for this impromptu interview, and wish everybody at PASC a good time. Thank you very much. Thank you, Chris.
Thank you.
Yeah.